So before joining Virginia Tech in 2018, he worked as a postdoc at MIT from 2017 to 18. He received his PhD from MIT as well in 2017. And before that, he obtained his bachelor's degree from Peking University in 2011. And his research interest is at the intersection of power electronics, microelectronic devices, and advanced materials. And he's received the 2017 MIT Microsystems Technology Doctoral Dissertation Award, the 2019 IEEE George Smith Award, and he has authored a lot of very exciting papers, journal papers, and conference proceedings. So with that, I would like to invite Dr. Zhang to present his work on ultra-wide bandgap devices reshaping the power electronics landscape. Yuhao?
Yeah, sure. Yeah, thank you very much for the introduction, Shrimp. Let me share my screen and. Can you see my screen now?
Yeah, looks great.
Okay. Okay. Yeah. Excellent. Hello, everyone. It's a really honor for me to present some of my research work, and I hope one day I can just visit the University of Utah, like in person. Okay, so the topic of my presentation today is the wide bandgap and ultra wide bandgap devices reshaping the power electronics landscapes. Yeah, so let me start by first introducing like our center is called the Center for Power Electronics, CPES at Virginia Tech. So that's one of the largest power electronics research centers and university-based research centers in the United States. And it was founded by like Professor Freddy, and now director is Professor Dusan Borovich. And we have like 7 tenure track faculties. And this is a really like a center with a long history, about like over 30 years. And traditional is mainly working on the circuit systems. And after I joined the center, essentially our center is new to the device and semiconductor research. Okay, so what is the power electronics? So power electronics is a conversion of electrical energy with solid-state electronics. So essentially, it's for example, convert the AC like power to the DC power, and changing the voltage, stepping up, stepping down the voltage. And essentially, easy way basically to group different power electronic applications is by their voltage class. So like typically in the device community, any power electronics below 600 watts is called the low voltage. And the example could be like our laptop chargers. And between the 600 watts and 1.7 100 watts, 1.7 kilowatts, that's typically the medium voltage range. And that essentially accommodates several very exciting like applications such as electric vehicles and data centers. And higher than 1.7 kilowatts is the high voltage. And this is usually the kind of the grouping the device community, and in the power electronics community, typically the medium voltage power electronics applications all the way goes to about like 10 kV. And the power device itself is a market size of about like $30 billion. And here I introduced two very exciting applications of the power electronics, and one is in the electric vehicles, and the other is the data centers. So essentially, the power devices are used in quite different systems within this like the electric vehicle. For example, the front panel will essentially for the display, and also the power management for this onboard charger and the battery systems. And also in the powertrain inverters, essentially kind of convert the electricity from the battery to drive the motors. And for example, this is the like a recent utilization of the silicon carbide like power devices, which is a wide bandgap semiconductor device that I'm going to introduce very soon in this Tesla Model 3 like inverter. So Tesla was one of the first like electric vehicle companies essentially utilize this like a wide bandgap semiconductor devices. And for example, in one of the applications is a powertrain inverters, and typically the devices with the voltage range of 600 volts, 1.2 kV, usually like needed, and that typically consists like about like 1/3 of the cost of the total power systems. So that's like electric vehicles. And another example is the data centers, and which is the hardware foundation for the artificial intelligence and cloud computing. And so currently, like the total like, electricity consumed by data centers is about 10% of the total electrical power in the world. So, for example, in these data centers, and the electricity or the power from the grid is typically 480 volts AC in the United States. And this power needs to be stepped down the voltage all the way to 1 volts DC to drive the CPUs and also the GPUs. And essentially, this kind of a power conversion or the power delivery is made possible by different buses or stages, and in each of these stages, essentially the power devices is the key enabling device. And in today's this power delivery from the 480 volts AC to the 1 volts DC, the overall efficiency is actually not very high. So just about like 70%. So essentially, you can imagine a lot of the energy is just lost in this like power conversion. Okay, so how do the power devices work in this power electronic circuit? And very simple, they work as switches. So ideally, the ideal power devices should conduct any amount of the current in its on state and block any amount of the voltage in its off state, and can switch at any frequency. But in the real world, the practical device, and typically they will have a finite amount of the on resistance, a finite amount of blocking voltage, and a finite amount of the switching frequency. So essentially, how to make them like devices which can like accommodate higher current and block higher voltage and switch faster. And the first thing we should do is to choose right materials. So here just to show several like key material properties that will be desired for these power devices. For example, the critical electric field, which is the maximum electric field that the material can withstand. And also the bandgap of devices, the materials. Typically, the higher bandgap will be desired, such to allow the higher temperature, high voltage applications, as well as the like high thermal conductivity and also the mobility and the saturation velocity, and those are relevant to the high current, high frequency. Okay, so now let's look at what silicon can offer us. And then one of the wide bandgap semiconductor, the silicon carbide, which has a bandgap about 3 eV, and another wide bandgap semiconductor, the gallium nitride. So essentially from here, you can see that the gallium nitride and the silicon carbide are essentially much superior power semiconductors compared to the silicon. Okay, so how does that benefits translate into the power device performance? So in the power devices, usually we prefer the devices to have small on resistance as possible, such to when conduct specific current, the conduction loss will be low. And at the same time, we want the device to be able to block high voltage. So if we just plot like the on resistance as function breakdown voltage, we prefer devices like towards the right bottom corner. However, there is a fundamental trade-off between this on resistance and the breakdown voltage. So this is not very difficult to understand if we just think about one like a thin layer, for example, semiconductor layer. So if we want to achieve the high breakdown voltage, we want to have the lower doping concentration and make this layer as thick as possible. And that will certainly increase the on resistance. So it turns out that this trade-off between on-resistance and breakdown voltage is related to the material properties, semiconductor material properties. So this is the silicon limit. This is the silicon carbide limit. This is the gallium nitride limit. So for example, if we compare the gallium nitride limit with the silicon limit, so for the same breakdown voltage, let's say 1,000 volts, and gallium nitride devices can achieve like 1,000 times lower special on resistance. So how does this like 1,000 times of especially on relation impact the device and system performance? So on one hand, if we make the devices with the same die size, and that essentially means the on relation will be much smaller, and when the conduct the certain current, the conduction loss will be smaller. Or the other way is that if we want to build the devices with the same on relations, then if the lower spatial on relation means the die size will be much smaller, and which means the capacitance and the switching charges will be much smaller. And that means that when we switch one time of this device and turn on or turn off, the total energy loss will be much smaller. So as a result, then essentially the device can switch at a much faster, much higher frequency, and it can also allow much lower power loss. Okay, so how does this frequency scaling up impact the system level performance? So this is just like a picture of like relatively high power like power electronic systems. So one thing you will find is that you barely can see the device in this like board, right? Because because actually the volume or the size of the power electronic system are actually dominated by this passive component like the inductors or the capacitors. So essentially, if we can scale up the frequency, then essentially it just allows a significant reduction, like in the capacitors and inductance that will be needed for the power electronic system. And overall, the system size and weight can be greatly reduced. So this is an example by using the silicon carbide devices in this Formula E like a vehicle. Essentially, the overall weight and the weight and the size of the system can be greatly reduced. So it should be noted that device is just a very similar size. It's just like packaging the standard package, and the device like size itself is just nothing compared to the system size. But it essentially allows this system level benefits by scaling up the frequency. And this is another example. So for example, this is the fast charger and using the gallium nitride devices, and this is some like gallium nitride based fast chargers, and this is essentially you can purchase on Amazon. Okay. Okay, and for the industry-wide, and the web Bandgap devices can just revolutionize the power electronics manufacturing paradigm. So traditionally, like all this manufacturing of the inductor, for example, is relies on the manual like manufacturing. It's a very kind of a labor intensive industry. But with this, for example, the gallium nitride devices, and now because the inductance just need to be much smaller, and essentially the inductors can be manufactured in the same way as the circuit board in a very integrated way. So essentially, the whole manufacturing paradigm, of the power electronics industry, can be going from the labor intensive to the automatic manufacturing. And here shows the cost perspectives. So if you compare the single the cost of the single wide bandgap devices with the similarly rated silicon devices, the wide bandgap devices the cost will be higher, but the overall system level cost could be much lower. That is due to the reduced size, weight of the passive components, and the reduced system cooling. Okay. So now I'm going to introduce two wide bandgap power devices that have been commercialized, and the one is called the gallium nitride HEMT, high electromobility transistor, and on the right this shows the silicon carbide MOSFET, power MOSFET. So let's first look at the gallium nitride HEMT. So that's a lateral device, and essentially the current just flow from the cell through the drain on one side of the wafer. And there's a key feature of this HEMT is that it has a two-dimensional electron gas channel, which is just a quantum well channel, essentially allow the very high like electron mobility. And so electron are essentially confined this two-dimensional conduction, has a very high mobility, and because this is a lateral device and it's easy like to be integrated with the ICs and also allows high-speed switching. But the drawback is that if we want to make a very high voltage devices, essentially we need to increase the gate to drain distance such to support a high voltage. And that essentially will make the chip size to be very large. And the other thing is the current is just conducting in this very narrow channel of just several nanometers wide. So the thermal and electric field like management is relatively challenging. And the silicon carbide power MOSFET is essentially a vertical device, and it just use like inversion type MOS channel. The mobility is relatively low, and the vertical device is not very like suitable for the integration. But essentially, it can allow much spreading like distribution of the current and also the electric field. So essentially it favors to realize the high current, and also if we want to make the high voltage devices, we simply need to make this drift region to be much thicker and lower doped. And essentially the die size can still maintain to be very small. And also the like due to more spreading out like the electric field and the current distribution, the thermal management is typically easier. So that's why essentially the gallium nitride HEMT is now commercialized at relatively low voltage range from the 15 volts to 650 volts, while the silicon carbide is from the 600 volts and to 3,300 volts, and pre-commercial device is up to 10 kV. Yeah, so essentially, I'm going to introduce very soon is some of our recent efforts, essentially to also push GaN towards this medium voltage and high voltage range to compete with the silicon carbide. And on the horizon is several ultra-wide bandgap semiconductors, and they have the larger bandgap compared to the silicon carbide and gallium nitride. So that's why they call the ultra-wide bandgap semiconductor. They include the gallium oxide and the aluminum nitride or high aluminum composition, aluminum gallium nitride or the diamond. So essentially, if we look at the like the available wafer diameters, so the gallium oxide and the aluminum nitride, aluminum gallium nitride are available for the relatively large diameter wafers, and the doping of the gallium oxide, especially N-type doping, is more available compared to that in the aluminum nitride, aluminum gallium nitride. Okay, so yeah, so this is the scope of the research in my group, and essentially we do research from the physics materials all the way to the converter applications, and compared to some of research, for example, in a Schramm's group, and we're more focused on the device and the device design processing technologies, not going too deep into these materials and the physics side. So specifically, we'll work on the medium voltage, high voltage GaN devices, and work on the ultra-wide bandgap material devices, and also the application-oriented device reliability robustness. So here are several essentially overall questions driving like our research. For example, in the first part is the medium and high voltage devices. Is there a room for GaN? And is the vertical device dominate for GaN, or is a lateral GaN device still option? And then the second part is that essentially what new capabilities can the ultra-wide bandgap devices bring to the power electronics? And the third part is essentially we study the commercially available devices, and particularly the wide bandgap devices and all these device manufacturers shows pretty good qualification reliability data, but many of these industrial users still have many concerns in using these devices. Many of them are related to this ruggedness out of the safe operating area. So essentially, our research is essentially to explore the wide bandgap devices ruggedness in many of the abnormal events nearing the destruction they made. So today I'm going to introduce like mainly the first and the second part of the research in my group. So start with the GaN part. Okay. So essentially, when we talk about the vertical GaN, like the popular substrate and epi will be on the freestanding gallium nitride substrate. And that will be different from the GaN on silicon that is used in today's commercial like lateral GaN HEMTs. And of course, if we have these freestanding materials and have a zero lattice match and very low dislocation density, a lot of the benefits. And the price we pay for this a better material property is the cost. So essentially over the last several years, the cost of the GaN wafer has already been reduced quite a lot. And then now if we look at the wafer and the cost, the epi cost per area, and compared to the silicon, it's still like 2 times or 3 times higher than that of the silicon carbide, and of course much higher than the lateral GaN silicon. Okay, but despite this higher cost, essentially can really enable some of the new properties and that are not present in the lateral GaN HEMT. And one of that is it's called the Avalanche. So Avalanche is impactization and multiplication dominated breakdown phenomenon in the power devices. That's the most desirable breakdown mechanisms in the power devices, because it's a non-destructive breakdown, and also it allows the device to dissipate this a surge energy in the circuit through its inherent avalanching process. And in the lateral GaN HEMT, there is no avalanche capability. But in the vertical GaN, in the PN junction, essentially can have a very robust avalanche capability, and as robust as the silicon carbide commercial devices. Okay, and now I'm going to introduce several of the vertical GaN power transistors. The first one is called the CAVIT, current aperture vertical electron transistor. And this transistor still utilizes this two-dimensional electron gas channel. You see this aluminum gallium nitride and gallium nitride. So there is a two-dimensional electron gas at the side walls. And the current is confined by this barrier, the p-type layer, essentially to flow in this very narrow kind of a region to enable the gate control. So it still utilizes the two-dimensional electron gas channel. And the second one is just very similar to the silicon carbide and the silicon counterparts called the power MOSFET, especially the trench MOSFET. So essentially, there is a trench gate, and the current flows in at this inversion type MOS channel. And a few years when I was working at MIT, we proposed a new transistor called which leveraging some of the FinFET structure in the digital world. And essentially, the channel is just the N type, like the fins. So there is no P type at all in this transistor. And essentially, this FinFET can achieve the enhancement mode or the normally off operation by making this fin very narrow. So essentially, at the zero gate bias and the work function difference between the gate metal and the gallium nitride can enable the depletion of the fin channel. So the device will have the positive threshold voltage. And since there is no p-type and there is no reverse recovery charge, and no need for IP regals of this p-type, and a lot of the material issues related to the p-type gallium nitride can be eliminated. But essentially, this structure need the very careful electric field management design. Okay, so in 2017, and we demonstrated this 1.2 kV proof of concept device, and we used this fin width about 200 nanometers, and it achieved the normally off operation breakdown voltage up to 2000 volts. And then we spent quite some time, close to 2 years, and trying to fabricate these devices on the 2-inch GaN wafers. So finally, we it's a very painful process basically to fabricate the wafer level devices using the university fab. But finally, we're able to make some of the 5 amp like 1.2 kV devices, and each device has about like 700 fins, and can support on-state current about 5 amps. And this shows essentially our like fabrication process. So it's just like the starting from this fin, and then we just stack one layer by the other, and the first the electric and the gate electric, gate metal, and some spacer, and the top source. And here shows the scanning electron microscopy images, photos of our like structure. Okay. So this is just a benchmark of our like demonstrated the large array devices 1.2 kV and 5 amp. And in comparison with the commercial silicon carbide devices, silicon IGBT, silicon superjunction devices, and some of the GaN HEMT, and be demonstrated up to 1.2 kV, and also the some of vertical GaN devices. So essentially, if we first look at the chip area compared to, let's say, a silicon devices with a similar current rating, and you can see the chip area is about like 50 times smaller compared to the silicon counterpart. And if we look at the switching field of merit, that's a smaller, the better product of the on-resistance or total charges, and it's significantly better compared to the silicon carbide and silicon counterpart. And this device is also very interesting because it doesn't have a p-n junction, so it's just a very different from like many conventional like power like transistors. So we call it a junctionless like transistor. So for example, if we look at the leakage current, the breakdown voltage is no longer dominated by the p-n junction. And from our study, we show it's just a very like these short channel devices, and it has a dipole effect, and the breakdown voltage, for example, and many times controlled by this potential barrier in the fins. So essentially, like in a relatively wider fin devices and at a different gate bias, essentially we can observe two very different like breakdown mechanisms in a single device. And also the other interesting thing about this like on-resistance is it's a conduction in the fin. So basically in the fin like region, and there is a parallel conduction path in the bulk fin as well as this side wall MOS channel. But different from the traditional MOSFET, this side wall MOS channel is accumulation mode. So essentially from our study, and this is actually the accumulation mode MOS channel is dominate the device like current conduction after the device is turned on over this bulk fin channel. And also, if we just think about like switching performance, like capacitance of charges, particularly the charges is very interesting in these devices because it's just related to these interfin designs. So for example, when we switch on switch devices, we need to supply or extract the depletion charges in the drift region. So if we can remove the gate in the interfin region, then essentially we can supply the charge and using the source to drain current instead of the gate current, and such the switching speed can be much faster. So here just shows a comparison between the silicon IGBT, that's like a dominant medium voltage device today, silicon carbide MOSFET, and the GaN FinFET. So essentially, like the GaN FinFET doesn't need like the rectifier to enable the anti-parallel conduction in many of the power electronics applications. And also it can just allow like a switching frequency about 10 times higher than that of the silicon carbide MOSFET, 100 times higher than that of the silicon IGBTs. Okay. So essentially the fin is not, the fin MOSFET is not the only transistor that can leverage the benefits of this fin channel. And the fin can be also used to make the vertical fin JFET, the junction like field effect transistor. So here it's just a side-by-side comparison between the fin MOSFET that just introduced, and essentially has the fin plus the MOS channel in the fin region. And also on the right, this is the fin JFET, and essentially between interfin regions filled with the P plus region, and essentially this like a channel electrostatics is controlled by the lateral PN junction. So compared to the fin MOSFET, it doesn't have like the oxide in the channel region. And also because now we are using the PN junction electric field management will be easier and easier to also realize the avalanche. But the process wise, this is also very challenging, particularly on how to selectively introduce the P-type gallium nitride. And this is a device currently developed under development by this next gen, which is a startup company, based in the California and also like in New York. And this is they have their own GaN fab in New York. So over the last 2 years, and like my group also work with the next gen to help them with their like FinJFET development and the calcularization. And for that collaboration, we mainly do this circuit level like calcularization of their devices. Okay. So essentially, this is some of the latest results that essentially we kind of announced in last IEDM. And this is the large area devices, and this is like on the 4-inch like a GaN substrate, and basically if we look at the this is the transfer characteristics, and up to 200 degrees C, the threshold voltage very stable over 2 watts. And also, it realized the avalanche. That's the first demonstration of the avalanche capability in GaN transistors, like a textbook, like avalanche test, and essentially like in a circuit test in my lab. And the special on rate is about like 4 to 5 times lower than this like a state-of-the-art commercial like 1.2 kV silicon carbide MOSFET. Very robust avalanche, and we also did a double pulse test of their devices, and very fast switching speed, about 10 nanometers, and switch from the on-off from the 600 amp and the 4 amp. Also, the reverse recovery is very minimum. Okay. So it should be noted that this vertical GaN device can not only build on the GaN substrate, but also can be built on this very low cost silicon substrate. There are a couple of different ways to build these devices. The very early device is called a quasi-vertical device, which essentially means that one electrode is on the front side of the wafer, the other is essentially built on this deep mesa. So it's a quasi-vertical. And very recently, like a more popular way is essentially using this fully vertical, but by selectively removal of the silicon substrate and this insulating and a very defective buffer layer. So have a lot of the trenches on backside, and the device just like some of the MEMS systems. This is the vertical GaN silicon device is it just like harvests a very strong momentum in the Europe and Asia. There were a couple of the very large like programs like over 50 million currently in Europe, and in this vertical GaN silicon device development. Okay, so that's the vertical part. So it's a vertical, like again, the only option, and so that's an open question. And so over the last 2 years, and we also explore a little bit on another option to make the like medium voltage, high voltage lateral GaN devices. It's essentially still to utilize this lateral device, utilizing this high mobility 2-deck channel. But in the vertical devices, essentially the key is to make the current distribution very spreading out. So how we can make the current like distribution also spreading out in a lateral device? Potentially, we can essentially enable this by having multiple stacked 2-deck channels in a lateral device. So essentially, we focus on these multi-channel lateral devices. So for example, this is the wafer grow by our collaborator. That's an increased semiconductor. And that's a 4-inch aluminum gallium nitride wafer on sapphire with a 5 stack of 2-deck channels. So essentially, the shear resistance can be 5 times lower than the single 2-deck channel. But the challenge is that now how to control all these channels, particularly the buried channels. And for example, if we make a diode, how to control the leakage current and do the electric field management. Okay. So essentially, last year, we proposed and for example, to use the P-type gallium nitride and to manage the electric field and leakage current in this multi-channel diode. So for example, here just shows the Schottky barrier diodes. And the traditional way to manage the electric field is by having a field plate at the anode side at the Schottky region. But last year we tried this using the P-type gallium nitride, essentially for the edge termination. There were a couple of benefits, and the first one, it doesn't have like a dielectric and the GaN interface, so many of the instability issues can be avoided, and also it's not very sensitive to the geometry designs, for example, the dielectric thickness, field plate length, etc. And potentially can allow the whole injection, which essentially can make the device, for example, sustain very high surge current, etc. And also, it's just compatible to the P-gate HEMT process, and for example, in all today's like gallium nitride foundries. So we make this structure and we demonstrate the breakdown voltage all the way to the over 3.3 kV, and with a pretty good like special arm resistance and the leakage current in the 10 to -5 amps. So very interesting thing after we demonstrate these devices is that now essentially we can calculate the the practical limit of these lateral devices, which is the trade-off between the special unrest and breakdown voltage. So if we can essentially manage the electric field very well and achieve an average electric field between the anode and the cathode, or in the transistor, for example, between the gate and the drain, to be about like 1 megawatt per centimeter, then essentially you see the performance limit of the lateral GaN devices can essentially be moved from close to the silicon carbide limit, that's a single channel practical limit, to the multi-channel limit is really close to the vertical GaN limit, and particularly at the voltage over, let's say, 2000 volts. So that essentially just shows this promise of the multi-channel devices for the medium and the high voltage applications. Okay, and like later last year, and we essentially put a little bit more complicated structure into this multi-channel diode. So in addition to having a P-type like a PN junction, essentially in the vertical direction. So now essentially in the anode, we make a couple of different things, and we wrap all these things with the PN junctions. And here we just utilize a P-type oxide, nickel oxide, and to essentially wrap all these multi-channel, multi-2-deck things. So essentially to wrap all these like 2-deck things with a PN junction for the electric field management and the leakage current control. And with that, basically you can see like we're able to lower the leakage current by about over 1 orders of magnitude, and at the same time push the breakdown voltage and to over like 5,000 volts. So that essentially represent performance exceed the silicon carbide unipolar limit. Okay, so here just shows the the performance benchmark. So for example, the medium voltage, high voltage. So this figure just shows for the like medium voltage, high voltage Shogi barrier diodes, and the purple like triangle here shows the silicon carbide and Shogi barrier diodes, or the junction barrier Shogi diodes, and this is our like multi-channel lateral GaN devices, and also some of the vertical GaN devices. So as you can see, this multi-channel lateral GaN like Shogi barrier diode can really exceed this silicon carbide like limit. And for the transistor and the orange triangle here is the commercial silicon carbide MOSFET. So if you see next gens like the like Fin-FET as well as the our Fin-MOSFET, and they both can offer about like 1 order magnitude smaller special on radiation compared to the similar rated silicon carbide MOSFET. Okay. So that's the state of the art of the medium voltage, the high voltage, the GaN devices. And I would also to have your attention on this yellow, on this green like symbols. This represents the state of the art of the ultra-wideband gamma oxide, the diodes and transistors. Okay, they are still about like 1 or 2 orders of magnitude like higher or the inferior like performance compared to the state-of-the-art GaN or silicon carbide devices. Okay, so next I would like to introduce some of the my own perspectives on this ultra-wide bandgap material devices. Okay, so the gamma oxide devices, and here just a state of the art of some of the power devices, and they can be made in the like lateral devices, and for example, up to like 8,000 watts. Of course, the special on-radiation is super large, and some of the like lateral gamma oxide Shogi barrier diodes, and also can be made in the like in a vertical way. For example, this is the like a vertical power Fin-MOSFET that Cornell demonstrated, very similar to our like GaN devices, and also the gamma oxide vertical diodes. Okay, so what are the some of the challenges like for meeting the theoretical limits of the like ultra wideband gamma oxide this limit? So now I just provide some of the perspective from the device point of view. Okay, so one of the the challenges about this drift region design. So most of the gamma oxide devices, let's say vertical devices, now are based on this non-punch through electric field design, which essentially for example, if you look at the electric field and distribution, that intentionally use very lowly doped drift region to maximize the breakdown voltage that people can get from this drift region thickness. But that's at the price of the higher on resistance. So if you look at the punch through design, the limit, which is actually much inferior compared to a non-punch through design. Okay. And also the challenges about the electric field management. So in the real devices, and the peak electric field in the devices is typically much smaller than the claim the critical electric field of the gamma oxide. And also this substrate is typically have a very large resistance. So in the 2 years ago, and in the 2019, and we basically demonstrate this vertical gamma oxide Schottky barrier diodes, and by combining several different design considerations. So for example, we use a non-punch through design with a relatively high doping concentration and drift region, and we made a new field plate design, which has a very small bevel field plate, essentially can allow the spreading of the electric field. And then we demonstrate the a better performance compared to the state of the art at that time. Okay. And then we test these devices at the high temperature and all the way up to the 600 Kelvin, about 350 degrees C. And we just test them to the 500 watts, and we see that all these diodes is very robust. It can just block very high voltage at high temperature. And then we compare the maximum temperature these devices, for example, can like sustain also the reverse bias. And we demonstrated that essentially these devices have the lower leakage current and similar rated silicon carbide GaN devices, Schottky barrier diodes at a high temperature. And also, of course, we also studied some of the leakage current mechanisms. It's also very interesting. Okay. So from that, we had a feeling that those gamma oxide devices potentially they are very stable, or at least better thermal stability compared to silicon carbide and gamma nitride devices that probably benefit some of the inherent properties of ultra wideband semiconductor. So how to exploit this potentially high thermal stability of the gamma oxide devices? By overcoming, at the same time, the gamma oxide itself has a very low thermal conductivity. That's like 1/10 of the silicon and about 1/20 of that silicon carbide. So that packaging level thermal management is essential. So in the last about 1.5 years, we are essentially studying this how to package these gamma oxide devices. And until very recently, we demonstrated this experimental prototype of the packaged gamma oxide devices. So this is this is one type of the packaging is relatively conventional. Well, essentially it's a packaging at the bottom side, just very similar to this TO series and packaging. The other way is we flip chip like the gamma oxide devices and do the double side packaging. So essentially the heat can be also extracted directly from the junction, the Schottky junction. And this is the some of the dies, large area dies we fabricated, and this is the image of the a double side cool package gamma oxide devices. And in these applications, and we test the surge current, the ruggedness, because that's essentially a way to measure how high the maximum temperature that this package device can withstand in a transient. And also, it is also the ruggedness that is designed in the power devices, is including any power diodes data sheet. So we build up this surge current circuit, and according to the JEDEC standard, and we test the our package devices in this circuit. So in this about 10 millisecond transient, and essentially we put you see we put the both sides which is about 1 millimeter thick silver plate, and with this within this transient, this 1 millimeter silver plate will just infinite heat sink. So it's just a little bit different from the steady state. Okay. And you see, this is the IV characteristics of our package devices. Can give a current up to at least 20 amps, and then testing our circuit. And for the bottom side cooled package device, and can sustain up to about 40 amps, and until the device failed thermally. And for the double side cool device, and can sustain a current, surge current, peak surge current up to 70 amps. And we also measure the devices every time after a single surge current test. And from here you can see the no degradation of the Schottky contact and the packaging up to the surge current 60 amps. Okay, and here shows the the simulation result that essentially illustrate why this double side cooling allows the higher surge current. So here is the simulated the heat flux in this double side cool structure. This is a flip chip structure. So on the bottom is the anode. So from the heat flux, this is the zoom in region of the entire structure. So basically, we can see most of the heat is just extracted directly from the junction, and very few are actually extracted through the up way, which is going through the gamma oxide substrate. And if you look at the peak temperature, and now it's within the gamma oxide. And in comparison, this is the bottom side cooling, and the anode is on the top. And most of the heat, almost all the heat, essentially has to extract going through this very high thermal resistive, like a gamma oxide substrate. And the peak temperature is right at the Schottky contact. Okay, and if we do the benchmark and of the surge current like capability with the commercial silicon carbide devices, then we saw some very interesting like findings. Okay, so here this is the commercial silicon carbide like Schottky barrier diodes, and with a different rated current. This is the maximum surge current that we tested on our same like a circuit that we built, and this is our like gamma oxide Schottky barrier diodes. So essentially, if we look at this maximum surge current over the rated current, then the gamma oxide devices can actually like offer a better like higher surge current capability compared to silicon carbide commercial silicon carbide devices, despite the much lower like thermal conductivity of the gamma oxide. And that is attributed to two different key metrics. On the device side, the on resistance, like the temperature coefficient of the on resistance, will be much smaller in the gamma oxide compared to that in the silicon carbide. So the on resistance just increase much slower, like in the gamma oxide, with the temperature in the gamma oxide. And the packaging side, by using this junction cooling, then essentially we don't need to extract the heat through this gamma oxide like substrate. So finally, let's look at several like different ways like for the further improvement of the ruggedness of gamma oxide devices. The first way, if we look at the substrate thinning. So for example, here shows the maximum junction temperature and the peak surge current. If we use the 800 Kelvin, for example, as a standard for the surge current, and this is the silicon carbide, like the Schottky barrier diodes. And basically, if we look at the gamma oxide devices with two different substrate thickness, and not too much different. And if we use the junction cooling, which is a double-side cooling package, that can essentially provide a strong boost in the surge current capability. And this is because, and also if we change the substrate thickness, not too much difference, because most of the heat doesn't go through the substrate, doesn't go through the gamma oxide substrate. So it basically makes no difference for the substrate thickness. However, if we just bond the gamma oxide layers to the silicon substrate, they're essentially leveraging both the high thermal stability of the gamma oxide junction and the drift region and the high thermal conductivity of the silicon carbide substrate. Then essentially we can enable the heat extraction in both ways and provide additional boost in this like a surge current capability. So from this work, and we really think now the gamma oxide devices may provide some new capabilities. So it should be noticed if we compare this special on-resistance breakdown voltage and the trade-off in our gamma oxide devices is still much inferior compared to silicon carbide devices. But despite this some higher on-resistance, it can provide like higher like surge capability or the electrothermal ruggedness. So it can be like suggest like some of the new like applications and for example the fall protection in the grid. Okay, to summarize my work, and essentially the silicon carbide and lateral GaN, and it's already being commercialized, and it's put into the application at unprecedented speed, and some of the robustness will be the last barrier for this application. And for the gallium nitride medium voltage, high voltage devices, and personally, I think both the vertical device and multi-channel lateral device are promising. And the industry's medium voltage vertical GaN transistors already outperform silicon carbide commercial devices, and the multi-channel GaN high voltage diodes exceed the 1D silicon carbide unipolar limit. And the very interesting thing is that this GaN device is a very different devices. For example, the multi-channel devices, this FinFET, there is no silicon or silicon carbide counterparts. And finally, for the ultra wide bandgap and the faster progress, but if we just look at the breakdown voltage, especially on release and trade-off, it's still not very competitive compared to the silicon carbide or gallium nitride. But I think the ultra wideband can bring some distinct capability for the power electronics applications, and that will be like definitely worth like exploring. And for those explorations, like the new materials device technologies will be needed, and also many times this material device packaging optimization co-design will be needed. Okay. And at the very end, just thank all my students in my group and all the sponsors that support like research in my group. Thank you very much.
Great, thanks.
Oh, that was an outstanding talk. I just have my mind blown. I think you found some new applications and niche attributes for using ultra wide bandgap semiconductors, and while also highlighting this is so good. I mean, I just love this seminar. So thanks again. Thanks, Yuhao. Let's maybe first go through the questions from students, and then I have a lot of questions we can chat even after the meeting. So any questions from students, you can just maybe unmute yourself.
There's one in the chat.
Okay.
You might hit that one first, and then students can ask after that.
Yeah. So do you want to read the question in the chat window?
Let me see. Probably I need to first stop sharing. Okay, and the chat. Okay. Is there any dependent on fin width on the breakdown voltage of the vertical GaN FinFET? Oh yeah, that's a very good question. So the answer would be like if the fin width is sufficiently narrow, which means the potential barrier in the fin channel is sufficiently high, there is no short channel effect. Then with the proper electric field like management, then the breakdown voltage should be determined by the edge termination. So there is no dependence. But if the fin width is not sufficiently high, sufficiently small, and then there could be the punch through, which is dominated, breakdown will be dominated by the potential, electrostatic potential in the fin channel. And in that mode, the breakdown voltage will be dependent on the fin width. Okay. Why there's a shift in IV at low temperature, slide 32. Okay, let me share the screen again. 32. Okay. Let's see. Okay, why there is a shift in IV at a low temperature? So assume you mean the here, the IV at a low temperature. This is slide 32. Yeah, so this is mainly because this is oh, I see. Okay, yeah. So probably I think your question probably is related why the low temperature, the current dependent on the temperature is not very pronounced, but when it goes to higher temperature, there will be high temperature. Okay. Here, this is just limited by the measurement limit and by the instrument, the noise flow, and so actually, as you can see at the higher current levels, and the liquid current should see a dependence on the temperature. This is just limited by the noise flow of the curve tracer. Okay. the highest peak temperature about does the device fail after test? Yeah, that's a very good question. So yeah, so let's go to the yeah. So that's a very good question. So basically, this is this is simulation corresponding to this 68 amp. So basically, from here you can see the after each like surge current like test in the circuit test, and we always do this curve tracer measurement, and particularly look at this subthreshold region, and so up to this like 68 amp, and device shows no failure. So it essentially fails at the peak current about like 70 amps. So which means that particularly during this transient, and the gamma oxide will be confidently sustain like peak temperature up to 800 degrees C without any problems. Okay. You mentioned that the lateral multi-channel again can reach GaN limit. That is depend on the number of the channels. At what point does the improvement saturate? Yeah, that's an excellent question. Yeah, let's go back to here. Yeah, so theoretically speaking, if we stack more 2-deck channels, and definitely we can make the shear radius smaller, and so the total like 2-deck density will be increased. But it should be noticed that the total, if we don't do the delta doping at each of these 2-deck channel, the total 2-deck density won't increase proportional to the like the number of the 2-deck channels. So which means if we don't do this delta doping at each of the channels, so probably 10 channel devices probably just have like about 1.5 like times.
So these are basically majorly polarization induced channels. Is that what you're saying?
Yes, yes.
Okay.
And yeah, so the multi-channel device is very interesting, and I think there are many open questions. So I can share some of our experimental observations. So we actually test the material and the devices, and for example the wafers with the like a delta doping at each of the 2-deck channel, and also the wafer without. And with the wafer with the delta doping, surely like the unradiated shear radiation can be even lower. But the problem is it's just very difficult to manage the electric field and control the leakage current. It's very difficult to realize decent like voltage blocking characteristics. And why is that? And some of them I think is still unknown. But the baseline is that in our all current like devices like with the high performance, we actually use the wafers, multi-channel wafers without the intentional like doping. So all the essentially the channel be polarization induced, and probably the origin of the like 2-deck will be similar to that in the one single channel device, say, from the surface donors. Yeah, and the limit of the increased channel devices, I think that's an open question. Like nobody really knows.
So just so that I understand this, these are all lateral Schottky structures, right?
Yeah, these are all the lateral Schottky.
Lateral Schottky. Okay.
Yeah.
So that's why you're able to deplete from the side, right?
Yes. Yes.
Okay.
Yeah. Okay. And if you do go, are we free to drop off? I have a back to. Okay. That's.
I think the answer to Suzette is yes. I think the Steve, when does a seminar get over formally?
10 or 15 minutes ago.
Oh wow, okay. So yeah,
So
Yeah.
Students are probably dropping off anyway, which is fine.
Yeah.
But yeah, we can keep the Q&A going as long as there's a Q and there's an A.
Yeah.
Okay.
Sure thing. So I saw there's a question on the chat. Is the in the top bottom cooling technique for GaN MOSFET, you mentioned GaN MOSFET substrate thickness, no effect on surge gap bonding to help significant for most of it doesn't flow through the and how second. Okay, that's an excellent question, and I can explain that. And
students are asking 2 detailed questions. So everyone paid attention to your long seminar.
yeah, I'm glad. And
this is great.
So yeah, let me probably look at here. Okay, so suppose we have like this double side cooling package. Then how much like heat will be distributed directly from the bottom, and how much going through the substrate? It's just purely determined by, roughly saying, is by the like comparison of the overall thermal resistance of the 2 different paths, right? So one is through the GaN MOSFET substrate, and the other is like through this nano silver. This nano silver is not like ideal. I mean like this is the sintering, because in the sintering there are also many like interfaces. So I mean the thermal resistance is not that low. So essentially, if this GaN oxide substrate can be changed, let's say, to the diamond or the silicon carbide, then essentially from our simulation, essentially just to predict the heat extraction like upwards, that path will essentially have an effective thermal resistance similar to the bottom. So essentially, the heat can be extracted from both the like upwards path and also the bottom path. So in that regards, and then the thermal resistance of the upwards path will matter. So that's why if we change to silicon carbide like a substrate, and then here just shows like the bottom and the double like cooling. So the bottom cooling means that all the like heat, it has to extract through the silicon carbide substrate. And in this regard, it basically shows that if we can transfer to the silicon carbide substrate, even just with the bottom cooling, it can provide a pretty good surge current capability. And in this time, like if we do the double side cooling package, probably the improvement is relatively incremental. So how much that this double side cooling can benefit compared to the bottom side cooling really depends on the like intrinsic like thermal resistance of the substrate. So that's why in the silicon carbide devices, and there is not too much need for this double side cooling, because it just do not like like bring too many additional like benefits. Yeah.
Great. So I have noted down a bunch of questions, but maybe I'll ask a few here and take the rest offline with you.
Sure.
So is there any other comments or questions from students? Okay, so you have I'll ask 2 questions here, and then I'll send you a separate Zoom link and we can chat.
Yeah.
So if you have the time, I know it's pretty late in the East Coast, right?
No problem at all. Yeah.
Yeah. So one quick question is, you compared the surge ruggedness of silicon carbide and gallium oxide, right?
Yes.
But gallium oxide does not have, I mean, it's a simple vertical Schottky structure, but silicon carbide probably, does it have anything built in the structure for surge ruggedness? Like, is that a fair?
Yeah.
So you're already showing that gallium oxide is better than silicon carbide, right? But maybe it's even better, right? That's what I'm trying to get at.
Yeah, that's an excellent question. So basically,
like what is done in silicon carbide for surge ruggedness?
It's essentially done mainly by using it's called the MPS, merge the PN, like
Okay.
So in silicon carbide, I would say the highest surge current capability can be realized, by sacrificing this unipolar switching like characteristics.
Okay, so basically you do a merge spin, so inject holes, and
Yes.
that slows down the device, right?
Yes, and even in the commercial silicon carbide Shocky barrel diodes, it's called a Shocky barrel diode, but actually it's a JBS, it's a junction barrel Shocky.
Right.
So
Yeah.
so still there is a hole like injection. Yeah.
That's great. So a quick question, like you mentioned about making vertical transistors on silicon, right? So wouldn't dislocations kill you?
Which one?
Like vertical GaN transistors, like FinFETs. Like if you make it on silicon substrates, won't the dislocations kill you?
Yeah. So basically, from the PN junction diode, that's another thing which is very interesting. Okay, so the decay current is higher. It's depending on the for example, if it's like a VIH or like a variable range hopping like decay mechanisms, and typically the dislocation density one order of magnitude higher than the decay current one order of magnitude higher. And the breakdown voltage is dominated by some of these trap like phenomena. So so the real interesting thing is that in this fully vertical GaN silicon PN diode, so if we measure like it on the curve tracer, like we won't see the avalanche breakdown. But if we measure on the circuit, if a package device measure on the circuit, it can just show the perfect like avalanche. So this is essentially we found this is because like in the circuit like test, immediately like there will be high current, like concurrent like presence of the high current and the high voltage, and the high current immediately just fill all the traps.
Okay.
So the further like the avalanche will be directly dominated by the junction. But if we measure on the curve tracer, because it's a quasi-vertical like measurement, then they just gradually just fill the traps, and then the breakdown voltage and is dominated by some of the traps in edge termination region.
Okay.
Yeah. So those are the answers. So the leakage is indeed higher, but in a circuit, like the avalanche can still be like demonstrated.
That's great. I mean, that basically means you can do it on silicon substrates and even further reduce the cost. That's great. So one last question, and then maybe I'll send you a separate Zoom link if you have time. We can chat. So you mentioned about this is a very simple question. So basically just for me to learn. And the students also. So for EV applications, right? For electric vehicle applications, you mentioned the voltage range for the power device. So what is the current drive that's required for those applications?
Yes.
Like what is the range? Like, yeah.
So, so the currently like they were roughly saying there were 3 main application scenarios like for the power devices in the EV. The first one is the like power management. That's for example, the front panel is 12 volts, and like there is also one like directly from the battery is usually 200 volts, and so there is one like a 200 volts to the 12 volts DC to DC, and that is typically utilizing the 600 volt devices. That's one. The second scenario is an onboard charger. So that is currently that DC bias is also 400 volts. So the dominant device is a 600 volts as well, 650 volts. And the last one is really in the like in the powertrain inverter. That's the one like interfacing the battery to the motors. So that part, the current voltage, bus voltage is still 400 volts, and the like the devices is 650 volts. That's why like recently most of the silicon carbide vendors just a pull forward is a 650 volts silicon carbide MOSFET. That's particularly for that applications.
Okay.
But the future trend will be used the 800 by voltage. That'll be 1200 volts device for that. So the powertrain invert application. So basically GaN currently is penetrating into the first two application scenarios, but for the third one, many people like have a lot of concerns. That's mainly because the last scenario, the powertrain, because the load is that machine, the motor, the Avalanche short circuit ruggedness is it's very critical, but the GaN is relatively lacking on that aspect. So the third one is still I would say like on debating, but the
Right,
first
right.
two.
So again, this is really good. We have a very good overview of the things, right? But what kind of current ratings do we need? I mean, you talk about the voltage, the blocking voltage, right?
Yeah.
But is it 5 amps? Is it like what range of currents are we looking at?
So for the first two ones, and like first of all, like the higher current, of course, the better. But for the first two applications, it's particularly for the let's say power management, and the first one it doesn't need to be too high, like just like a 10 amp device, 20 amp device will be good enough. For the powertrain, current module like typically using is like a 300 amp like module, like 200 to 300 amp like module, so silicon carbide. That's typically like 6 to 7 dies co-packaged into a module. Yeah.
Great. I think okay. One last question from student: does a silicon carbide SBD also have similar thermal management as the gallium oxide double side cooling?
Yeah, that's a good question. So that's actually something I just showed in my last slides. Is that so the answer is yes or no. So yes. So for the silicon carbide module, there were also many like advanced packaging, like including a double side packaging. Also, like for example, you can put the force fluid or gases on both sides. Definitely. But on the other hand, because the silicon carbide, the cheap material intrinsically have the high thermal conductivity, so many times it probably doesn't make too much sense to pay a lot of extra money to bring relatively small benefits. And the power electronics in general is very like cost sensitive industry.
Yeah. Great. I think that was a very lively Q&A. Any other questions or comments, or we can formally close the seminar. Thanks a lot, Yuhao. I mean, this was like so good. I enjoyed it, every bit of it.
Yep.
Thanks for the great talk.
Yep. Thank you. Bye.
Yeah.